Last video for Unit 1. Aren't you excited to go and write your test? It's a lot of stuff. But there is a practice test to practice. And just make sure that you've completed your learning assessment. And then the test is done online. I will say, please, please, please do not use any artificial intelligence to help you do it. You are going to be writing a midterm fairly soon, and that is an in-person midterm. I just, because I know this is a remote course, was trying to make your life easier. So treat the test like a test. Walk into it with just your data package. If you want to write something onto it or your information booklet, if you want to write information on there, feel free, but do not look things up in your notes. Don't go into the test unprepared because that's just going to make you feel awful when you go to the exam. The exam will feel overwhelming. Okay? So, anyway, sorry, that just was an aside. But what I want to look at is enthalpy diagrams for reaction mechanisms. So this is a multi-step reaction mechanism shown as an enthalpy diagram. So each step in the mechanism is going to appear as a bump with its own activation energy and activated complex at the top. So for example, here we've got reactants, we've got an activated complex at X1, and then we would have a product here on the valley, but we're going to call that a reaction intermediate. So I'm talking about the next part here. So we've got reactants at the top. You've had an activated complex, X1, and then it would go to products, which because those products are getting used again, we're going to call them reaction intermediates. This little bump has its own activation energy from reactants up to activated complex. Then for step 2, these I1s, the reaction intermediates, become your reactants. Then you've got another activation energy up to another activated complex, X2, and then your products would be your second reaction intermediates. And then this step, again, from reactants to activated complex would have its own activation energy. And then this is a 3-step mechanism because you're now taking your reactants, which are your reaction intermediates 2. They're going to go up to their own activated complex, X3, and then it's going to have a final drop to your products. This last step has its own activation energy from reactants up to activated complex. Then the key thing is that in this diagram, your activation energy overall would be from your reactants up to your highest peak. So if I want to draw this as like a simplified potential energy diagram, it would go from reactants up to the highest peak and then down to the products. So when we're looking at a simplified potential energy diagram, you're just taking out the steps and saying, okay, what's the overall activation energy? Okay. And then the other part is that your enthalpy or your heat change would be from reactants to products, right? Doesn't matter what happens in the middle. It's always from the beginning to the very end, and that would be your delta H between. So here's an example. Given the following potential energy diagram for a reaction mechanism, answer the following questions. First off, how many steps does this mechanism have? Well, reactants to products, there's 1 step. Reactants to products, that's 2 steps. Reactants to products, that would be 3 steps. So this is a 3-step reaction mechanism. If I asked you for the activation energy for the overall reaction, you'd be going from reactants to highest bump. So we're going to assume that highest bump goes up to 80. So the overall activation energy would be 50 to 80, which is 30 kilojoules. Every step has its own activation energy, but if we wanted to look at it, we could use that information to determine which is the rate determining step. So the RDS means rate determining step. So the slowest, and then which would be the fastest. So which one has the highest activation energy? That's going to be your rate determining step. And which is going to have the lowest activation energy? So that's going to be your fastest step. So you guys can see that step 2 would be my rate determining step. The activation energy for step 2 is all the way from here to here. So this is EA2. Whereas EA1 is going from here to here, and EA3 is going from there to there. Now, at first, I wasn't too sure which one was going to be the smallest, but when I drew it, this third one definitely felt smaller. I'm not quantifying it, I'm just looking at the sizes. And so, step 3 is my fastest step. Is the overall reaction exothermic or endothermic? Well, these are my reactants, these are my products. My products have more energy than my reactants, so it must have been an input of energy. So it's going to be a positive delta H, so it's going to be endothermic. If I wanted to find the actual energy, now I would give you a better graph on a test, but let's just say it starts here at 50 and then my products 68. So my delta H of my reaction is going to equal my heat of my products minus the heat of the reactants. So my products, I'm going to say, is about 66, 67, 68. It could be kind of up to you. I'm going to say 68. The heat of the reactants, I'm going to say, is 50. So my overall heat will be a positive 18 kilojoules. And then if I was going to do this as a reverse reaction, the delta H doesn't change. What does change is that it would be negative 18 kilojoules. And then the last thing, if I wanted to determine the activation energy for my reverse reaction, there's a couple ways of doing it. One, I could do EA forwards, right? So the forwards reaction is all the way from here to here. This is my EA forwards, whereas my EA reverse would be from the products up to that highest peak. So I could know that I called that about 68. So 68 up to 80 is going to be 12 kilojoules. Oops, I have to write the units again. Or I could have used the equation, which is EA forwards equals EA reverse plus delta H. So my EA in reverse would be EA forwards minus delta H, which would give you, my forwards was 30 minus the 18, which would also give me the 12, right? So from the graph or from the equation. And then my rate determining step for my reverse reaction, which would be what? So in the reverse, which one has the highest activation energy? So in reverse, this is EA1, this is EA2, and this is EA3. Which has the highest activation energy in reverse? Well, it's actually still step 2, I think. Awesome. Okay. So the last thing that we're going to do is just take a scenario and try our best to draw a potential energy diagram. So it says here, draw a potential energy diagram for a reaction mechanism with 2 steps. The first step is fast. The second step is slow. So the slow one is going to have a greater activation energy. The fast one is going to have a lower activation energy. The overall reaction needs to be exothermic. And I'm going to use labeled arrows to show the overall activation energy and the delta H for just the forward reaction. So I'm going to start off by drawing my axes. We've got potential energy on my y-axis, and then I've got reaction proceeds on my x-axis, something like that. Okay, and I want to do 2 things. 1, I want to make sure it's exothermic, and 2, I want to make sure I draw 2 steps between where the first step has a lower activation energy than the second one. So everybody's can look a little bit different than anybody else's, but I'm going to start up here just because I need to make it exothermic. So I could just start with reactants and products. Cool, that made it exothermic. Now I'm going to put 2 bumps in between, with my second bump being bigger. So I'm going to go up, and then I'm going to go up, and I'm going to come down, right? Not a perfect science. So then I wanted to show labeled arrows with my overall activation energy for the forwards reaction. So it's going to go from reactants to top of highest peak. So this would be my activation energy forwards. And then I wanted to show my delta H. So for this one, I could put my arrow down here. So it's anywhere between reactants and products. So I'm going to put delta H here. Awesome, right? So, first step is fast, it has a lower activation energy than my second one. Right. Overall reaction is endothermic. I've met all the expectations. Awesome. Well, I hope Unit 1 felt good. Like I said, go and make sure you've done all the practice questions in Hebden and the ones I supplied. Make sure you've checked your answers as you go, complete your learning assessment, do the practice test, and then you're ready to write the test online. But try to treat it like a test. I know I'm letting you do it at home, but there is a time limit, so you do have to know your stuff. You can't look everything up, and you will be writing an in-person midterm soon.